In this video, we'll be looking into backtracking topic. We'll understand the principal idea of backtracking. We'll be looking into n-queen's problem and sum of subset problem. So starting from the definition of backtracking, it is a systematic method of searching for the solution to a combinational problem by means of algorithm. So the problem that have exponential time complexity can be best solved using backtracking method. So these two are the important things: exponential time complexity problems and a systematic method of searching the solution to a combinational problems by means of algorithm. Understanding the principle idea of backtracking, so it is to construct solutions by selecting one component at a time and evaluate such partially constructed candidates. So at a time you obtain one solution, further you divide the problem, obtain one solution, and then backtrack it and check if it is the optimal solution or not. So we'll look into the principal ideas. So if partially constructed solution can be developed further without violating the problem's constraints, it is done by taking the first remaining legitimate option for next component. If not, if there is no legitimate option for the next component, then the remaining alternate component need not be considered. In this case, algorithm backtrack to the last component of partially constructed solution with its next option. So under this, we'll be having n-queen's, sum of subset, and Hamiltonian problem. So in this video, we'll be discussing the first two. Okay. So further we have the output of backtracking algorithm can be expressed as n-tuple. So we'll look into the algorithm first. So here I have the algorithm backtrack. So here I'm taking x of 1 to I. That is, this line defines the backtracking algorithm as a function which is named as backtrack that takes an array. This is an array from 1 to n elements having position up to ith element, ith position. Then it gives a template of generic backtracking algorithm ES. So the input here is specifies first I promising components of solution. Output is all tuples representing the problem solutions. If x of 1 to I is a solution, right? X of 1 to I. This statement refers that we are performing a condition check. That is, if the partial solution forms a complete solution to the problem A, then we return it as complete solution. Okay, right? Solution. We write the solution. Else, we look into the for part. That is, for each element x belonging to S of I plus 1, consistent with x of 1 to I, and the constraints do. That is, for each candidate we are checking if the set S of I plus 1 contains potential candidates for the next component of the solution. If this condition is true, the element x is only considered only if it is consistent with the current partial solution x of 1 to I. Okay, so that's what it means. If this condition holds true, then we extend the solution. That is, partial solution x is added to by adding new component x at the solution part I plus 1. Okay, this step is very crucial for writing the solution, as it is incrementally built upon. Then ultimately we return the backtrack 1 to I plus 1. That is, this algorithm calls itself repeatedly or recursively with the new extended solution. This is the solution. So it explores all the consequences of adding the new element x to the solution, searching for component solution from this part onwards. So here we can understand the backtracking nature of the algorithm. So this was about the algorithm. Usually they don't ask algorithm in the question in exam, but then if they ask, then you should be ready to write this part. Okay, understand this and write it again. Write it. So we'll look into this part now. So the output of backtracking algorithm can be expressed as n-tuple. So in this we have three main components, three main topics to understand. One is the state. The n-tuple x1, x2, xn, there are n number of tuples, is called as a state or solution of problem. So the state space is set of all possible states is called state space or solution space, denoted by S. Then we have state space tree. So this is the tree corresponding to state space is called state space tree. So its root represents initial state before the search of solution begins. Nodes of first level in the tree represent the choices made for the first component of the solution. Yes, the nodes of the second level represent the choice made for the second component, and so on. This is the root, and for this, these are the choices made, and this was the choice made for this question, this particular component, and these were the choices made for this particular component, and it goes on, okay, till the end. So our node in a state space tree is said to be promising if it corresponds to a partially constructed solution that may still lead to a complete solution. Otherwise, it is called as non-promising node. We understand by definition itself. Leaves represent either non-promising dead ends or complete solution found by the algorithm. This again depends on which problem we are dealing with. So let's quickly look into n-queen's problem now. So n-queen's is a pretty simple problem, I would say, straightforward answer. So the problem is to place n queens on a n cross n chessboard so that no two queens attack each other by being in the same row or same column or same diagonal. So in a given chess row, in a given chessboard, you should place the queens such that row, column and diagonal conditions should not satisfy. Okay, so I hope you all know how to play chess. So if I place a queen here, I cannot place a queen here because it is in the same row. This queen can kill this queen. Again, I cannot place a queen here also because it is in the same column. This queen can kill this queen, and I cannot place the queen here also because it is diagonal. So I should make sure that in a given chessboard, I should place the queen such a way that they are not being attacked by each other. So that's what n queen problem initially states of. So if I take n is equal to 1, I can place the queen anywhere, right? So it has a trivial solution. For n is equal to 2 and 3, we have no solution. But when we come to n is equal to 4, we can follow the further steps. Okay, so that is place one queen in one row. Yes, I placed a queen in one row. Assign a column for each queen on board present in figure so that no queen is attacked horizontally, vertically, or diagonally. So we have to consider 4 queens here. N is equal to 4 means 4 queens we are taking. Okay, Q1, Q2, Q3, Q4 in 4x4 chessboard. This is 4x4 chessboard. So we have to solve the problem using state space tree. That is, we will calculate or generate all possible outcomes for this particular problem. So let's see how will we place the queens, the 4 queens in this 4x4 chessboard. That is for n is equal to 4 problem we are seeing. Okay, so firstly, this is the chessboard. We know that this first row should be for queen 1. Second row should be for queen 2. Third row should be for queen 3 and fourth row for queen 4. So if I start from the first box of row 1, I can place q1 here, yes. And the second box also I can place queen. Third box also I can place queen, and fourth box also I can place queen. Firstly, let's look into this particular problem. If I place queen in the first box, let's see what happens. So if I place queen in the first box, I cannot place q2 here, nor I can place q2 here. So q2 could be placed here or here. So there are two possibilities of placing q2 here. So let me draw those two possibilities here. So q1 was here, q2 I placed here, q1 was here, q2 I placed here. Next, now can I play? Where should I place q3? q3 cannot be placed here, q3 cannot be placed here, nor here, nor here. So if you check at the third row, it cannot be placed here, nor here, nor here, nor here. So further, I cannot deduce to any solution here. In this part, I cannot place in first box, I cannot place in second box, I cannot place in third box, I cannot place in fourth box also. In this condition, I backtrack to the original problem and increment, look into the other option where I can place q2. So q2 could be placed here. Now I'll see. I cannot place q1 here. Q3 cannot be placed here. Q3 cannot be placed here nor here. This is the possible place where I can place q3. So I'll draw a box here for q3. So q1 was placed here. Q2 got placed here. Q3 was placed here. Now I'll check where can I place q4. Q4 cannot be placed here because q1 is the same row. It cannot be placed here. Q4 cannot be placed here because this is diagonal, and Q4 cannot be placed here also because Q2 and Q4 are diagonal to each other. In this condition, 1 I cannot in first box, second box, third box, and fourth box also. It is not possible. In this condition, I need to backtrack. I'll come in this position, this place. Now, here further, I cannot shift Q3 anywhere else. So again, I'll backtrack to this place. So here Q1 was in the first box. Now I'll shift Q2 in the second box and see. So that's where I come here. Okay, Q2 is in the Q1 is in the second box. Now it cannot be placed here Q2 nor here. Here or here, two possibilities are there of placing Q2. Let me check those two possibilities. This is the first box. First possibility, second possibility. Let me draw them. So Q1 I was here, Q1 was here. Now I have two options. I cannot place Q2 here also. Sorry, this is also wrong. So Q2 can be placed only in one box. Here it is placed. Now Q3, placing Q3. Q3 cannot be placed here, nor here, nor here. Q3 can be placed here. So I have one possible way of placing Q3. So Q1 was here, Q2 was here, Q3 was here. Now Q4 cannot be placed here, nor here, nor. So Q4 can be placed here. So if I place Q4 in this position, I would get Q1 here, Q2 here, Q3 here, and Q4 here. So this is one possible way of placing all the 4 queens in 4x4 matrix. So if I write 1, 2, 3, 4, 1, 2, 3, 4 here, the indexing 1, 2, I can place Q1, 2, 4, I can place Q2, 3, 1 is for Q3, and 4, 3 is for Q4. So this was one possible way. Okay, so if I place Q1 in first box of row 1, I cannot get the solution, so I backtracked. Then I placed Q1 in the second box and I obtained one possible solution, that is this, right? If I place Q1 in the third box, I will get mirror image of this, Okay, mirror image of this particular solution. That is Q1 was in 2, it will go to 3. Q2 was in 4, it will go to 1. Q3 was in 1, it will go to 4. And Q4 was in 3, it will go to 2. So here it would be 3, 1, 1, 3, sorry. It would be 1, 3 and 2, 1, 3, 4 and 4, 2. So these two are the possible solutions for the n-queens problem. So this was about n-queens problem. Let's look into sum of subset problem now. So here we have sum of subset problem description. So given a set of n positive integers, s is equal to s1, s2, s3. These are the positive integers we have. We have to find a subset of s whose sum is equal to a given positive integer d. So we have a integer d whose sum of subset s should be considered. S is the sum of integers from which we should deduce the subsets. But the subsets should be equal to the positive integer d sum value. Some of the instances for this problem may not have any solution. Okay. In order to solve this problem, we make use of state space tree as binary tree, where root represents the starting point with no decisions made about the given elements. So its left and right child represents the inclusion and exclusion of S1. So if this is the root node, this is S. Okay. S1 would say S1 is included. And here S1 says right side S1 is not included. This is inclusion of S1 and this is exclusion of S1. Coming to S2, again if we have 2, here S2 would be included and here S2 would not be included. So that is what it says. We record the value of S dash, the sum of these numbers in the node. If S dash is equal to D, we have a solution for the problem. If S dash is not equal to D, we can terminate the node as non-promising if either of the following two conditions is hold. So S dash plus S of I plus 1 should be greater than D if the sum is too large. If else S dash plus from j is equal to I plus 1 till n, we keep on updating the values. S of j is less than D if sum is too small. So this was about the sum of subsets introduction. Now we'll be looking into the problems, sum of subset problems. So here they have specified the S values, the set of integers which comprise of S1, S2, S3, S4, and the total sum value they have told it as D, that is 15. So I should start from 0. From 0 I'll start. First on the left side it should be inclusion of S1, and on the right side it should be exclusion of S1. So 0 here with 5 and here without, with 3 and here without 3. So first I will get 0 plus 3, I will get 3 here, and 0 without 3 is 0 only. So level 1 I did S1 is equal to 3. Next I have next level. Here I'll take S2 is equal to 5. That is with 5, here without 5, here with 5, here without 5. With 5, 5 plus 3, I get it as 8. And on this side without 5, that is I get it as 3 only. Here with 5, 5 plus 0 is 5. And here without 5, I get it as 0 only. So next, my next level. Here I'll take S3 is equal to 6. So with 6, without 6, with 6, without 6, with 6, without 6, with 6 and without 6. So quickly writing the values, 6 plus 8, I would get 14 here. And on this side, I have, here I'll get 14 and here I'll get 8, that is without 6. Here with 6, I'll get 6 plus 3, that is 9. And here I'll get 3 itself. Here with 6, 5 plus 6, I'll get 11. And here without 6, that is 5 itself. And here with 6, so I'll get 6. Here without 6, so I'll get 0. So I'm done with my third level. Now last I have fourth level, that is 7. S4 as 7. So here I have 2. Here I'll get 2. Here also I'll get 2. Here I'll get 2. Here I'll get 2. Here I'll get 2. Here 2. And here again 2. So 14 is there. Now with 7. 14 with 7 would be greater than 15, no? So I need not consider this. Now here 14 without 7. 14 without 7, I would get 14 only. I'll write 14 here. Now 8. 8 plus 7. 8 with 7. So I get 15 here. Next 8 without 7. 8 without 7, I'll get 8 itself. 9 with 7. This will be greater than 15. So I need not consider this. 9 without 7, I'll get 9 itself. 3 with 7. 10 I'll get. And 3 without 7, 3 only. 11 with 7, 18. So I need not consider this. I'll write 11 itself. 5 with 7, 12. And here only 5. 6 with 7, 13. And here 6. 0 with 7. So I'll get 7. And 0 without 7 is 0 itself. So if I look at the last level, the leaf nodes, I can say that only one possible solution I've got. That is 0, 3, 8, then 8, and then here with 7. So this is the solution states that for this particular problem, in order to obtain the solution, I should firstly consider with 3, then with 5, with 6, and without 6, and with 7. So this is the sequence. I should highlight this part. Okay, I've got 15 as my solution. So this was about the first problem. Let's look into the second problem now. So this problem is pretty lengthy, I would say. Not lengthy, but then it will have multiple branches. Okay, so let's start with it. So from 0, I have with 5. So I'll write 5 here. Here without 5, so 0. Next, I have 10. So with 10, so I'll get 15 here. Here without 10, so I'll get 5 itself. Here with 10, so I'll get 10 here. Here without 10, so I'll get 0 only here. So yeah, next I have 12. So with 12, here the limit is sum is 30. Okay, so here with 12, 15 plus 12, I have 27. Without 12, I have 15 only. Now with 12, so 15, 5 plus 12, 17 I have, and here without 12, so 5. Here with 12, so I get 22. Here without 12, so I get 10. Here with 12, so I get 12. Here without 12, so I get 0. Now further, I have 13. So 27 plus 13, I need not consider it. 27 plus 13 is, so it is 40. So I need not write it. Without 27 only I'll write. On this side I'll get 27. This side I need not consider. Now 15 plus 13, 28. So I can write 28 here. And without 15 also I can write. 17 plus 13, 30. So I have exactly got the answer 30. Now without also I wrote 17. 5 plus 13, 18 I got, and here 5 I wrote as it is. Here 22 plus 13, it won't happen, so I'll write 22 only. And 10 plus 13, 23, and without just 10 only. 12 plus 13, 25. I have 25 here, and again 12, just 12. Here 13 I wrote, and 0 I wrote. So I'm done with 30. Now I have 15. So 27 with 15, without 15, it will be 27 only. I cannot write further. 28 also I cannot write further. 15 plus 15, I get 30. One answer. Without 15, again 15 only. I need not write it again. Here 30 with 15, I need not write it. Without 15 also, I need not write it. Without 15, I'll get 30 itself. Next I have 17 plus 15, it will cross 30, so I need not write it. 18 plus 15, it will cross 30, so I need not write it. 5 plus 15, I'll get 30, so I can write this. Next, without 15, 5 only. 22 with 15, it will cross 30, so I need not write it. 23 also, it will cross 30, I need not write it. 10 plus 15, 25, I need not write it. 25 plus 15, it will cross. Here further, if you look, I need not write for any of the following, okay. So I'm done with my this level also. This was level 0, this is level 1, this is level 2, this is level 3, this is level 4, this is level 5. Now let's move on to level 6. So 27 level 6 not possible, here also not possible. 15 plus 18 not possible, 30 plus 18 not possible, 17 not possible, 18 not possible. 18 plus 5 not possible, 22 plus 5 not 18 not possible, 23 plus 18 not possible, 10 plus 18 not possible, 25 plus 18 not possible, but 12 plus 18 I would get 30. Yeah, and 12 here it will remain. So here 13 it will again cross 31, it will become not possible, and here 18 I will be left out with. So level 6 also is done. So if I have to write the solutions now, the subsets, here, okay, let me write. I have not written the subset here, right? So the subset would comprise of with 3, so 3, with 5, so 5, without 6, and with 7. So with this subset, I'll get this answer. Now for this, let me write the subsets. So here I'll get 4 subsets. So let me highlight those subsets once. So I started for this, if I have to write, I started with, for this, so let me write the subsets now. So S1, so here 4 subsets are there, right? So S1, first I took 5 was considered, then 5 was considered, then 10 was considered, then 15 was considered, I got 30. Second subset, if I have to write, I took 5, then I took 12 and I took 13. Then third subset, if I have to write, it was 12 and 18 only, this one. S3 this is. Next I have S4 as 5 I wrote, then 10 I wrote, and 15 I wrote. This I have written here only. So majorly I'll be having 3 subsets here. So that's what I've written here. So this is repetition. 5 without 10, 5, again 5, and 5 and 15. Here it will be 20. Sorry, this is not, we need not consider this. Okay, so we'll have 3 solutions here, not 4 solutions. So I hope you have understood sum of subset problem. So if you have any doubts, do let me know in the comments and subscribe to my channel. Thank you.